protein, digestion maybe or whatever, but this is kind of what an amino acid looks like. So there's the two carbons, two functional groups here, actually multiple functional groups, but this is an amino group. This is the carboxyl group, right? This is the acidic part of it here. In solution, as soon as you put this in water, this becomes the conjugate base. You lose that and it comes out of line. This R stands for residue. The body uses regularly 20 different amino acids in building proteins to make polypeptides. What makes those 20 different amino acids different is what's right here. It could be as simple as a hydrogen, or it could be this complex ring that contains hydrocarbon and sulfurs or whatever, right? I mean, that's what varies, is what's right here. So when you hear things like alanine, proline, tyrosine, valine, tryptophan, things like that, those are the amino acids. And what's different about all of those is not this part of it here, but this part right here. And if we take those amino acids and hook them to, oh, there they are right there. Oh, if you ever have taken, will take, or whatever, a biochemistry class, you will have to learn the structures of all of these and memorize their abbreviations and whatever. That's beyond the scope of what we need to do, but that would be something you would do in an upper division biochem class. You would do that. But these are the 20 regular amino acids that we would find in solution. We modify some of them to do other jobs. Sometimes we modify them just to become neurotransmitters and things like that. But as far as making a protein, we string those together in long chains. So when you look at a protein as a polymer of amino acids, it'll exhibit different levels of structure. If I just make that an amino acid, right, that would be a monopeptide, if you will, one of them. Two of them together would be a dipeptide. Three of them would be a tripeptide. But really what I'm thinking about making is something that is a big long chain of these. And if our goal is to, or what this polypeptide is going to be as a protein, this is probably at least 100 amino acids long, sometimes much more. It could be 300, 400 amino acids long. Most proteins are in the neighborhood of 100 to 300 amino acids long. This is a long chain of amino acids. And just this simple chain right here, this linear thing, is not functional. It doesn't do a job. It doesn't do anything. But this first level of structure would be what we would call primary, one with a superscript 0, the primary structure, the primary level of structure. If a protein is going to be functional, it has to have a three-dimensional shape. So it's going to have to fold and turn and twist and all of that to get 3 dimensions. The next likely structure that would form here is one of this. So as this starts interacting with hydrogen bonding along different groups in here, it's either going to make something that looks like this, which is a nice coil, a helix, or it will do something that looks like this, where the bonds will be like this. Like that. These are the bonds this way. This level of structure, we would call this alpha, because if I look at it on end, it spirals right-handed away from me. So this would be called an alpha helix. This would be called a beta pleated sheet, or it makes like a sheet. This is incredibly strong. To give you an idea of a protein that has a lot of beta pleated sheets in it, silk is a protein, silk threads, and they have a higher tensile strength, that is, if I start pulling them like this, than equal diameter steel. So they're incredibly strong. So that's why they used to use silk back in the day to make parachutes and clothing and things like that, is because it would last. It doesn't tear, it doesn't rip. It's a very strong protein. And the reason it's very strong is because it has a lot of these are all hydrogen bonds, just full of hydrogen bonds. This is the second level of structure. So this would be called secondary structure. 2 with a superscript. You heard of Linus Pauling? Maybe. Linus Pauling won a Nobel Prize for, he almost was the first to determine the structure of DNA, but he wasn't. And that's a very interesting story.